On April 24th, 1990, a $2.5 billion telescope was sent into space. A few weeks later, engineers discovered the disaster. The main mirror was damaged. The error was only 2 microns, the thickness of human hair, but it was enough to make all the images blurry. The most expensive telescope in the history of mankind has become a laughingstock. Newspapers wrote about the grandiose failure of NASA, but it was this failure that turned into one of science's greatest success stories. In 1993, astronauts went into space on a repair mission. 5 spacewalks, the most complex operations in orbit. They installed corrective optics directly into the telescope. And when the first corrected images came to Earth, the whole world froze. What people saw changed our understanding of the universe forever. Hubble looked into such depths of space that no telescope before him had penetrated. He saw galaxies that formed 400 million years after the Big Bang, practically babies on a universal scale. Each image is a time machine. When you look at a picture of a galaxy a billion light years away, you see it as it was a billion years ago. The famous pillars of creation in the Eagle Nebula showed the world how stars are born. Giant columns of gas and dust several light years high, inside which new suns form. These images have become not just scientific data, they have turned into works of art, into icons of the space age. Hubble helped to accurately calculate the age of the universe, 13.8 billion years. He discovered that the expansion of a universe is accelerating, not slowing down as previously thought. This discovery won the Nobel Prize and led physicists to come up with the concept of dark energy, a mysterious force that makes up 68% of all energy in the universe. The telescope photographed the deepest image of the cosmos in history. Astronomers pointed it at a tiny patch of sky the size of a grain of sand on an outstretched arm. They kept the shutter open for 11 days. The results stunned everyone. Almost 10,000 galaxies were found on this microscopic piece of empty, as it seemed, sky on this microscopic piece of seemingly empty sky. Almost 10,000 galaxies were found. Each galaxy contains billions of stars. This meant that if there is such a density of galaxies everywhere, then there are hundreds of billions of galaxies in the universe. The scale is simply unimaginable. Hubble witnessed cosmic catastrophes. In 1994, he observed the collision of comet Shoemaker-Levy 9 with Jupiter. 21 fragments of the comet crashed into the gas giant at a speed of 60 kilometers per second. The explosions were so powerful that they left dark scars larger than Earth. This was the first collision of celestial bodies that humanity observed in real time. The telescope has opened up the world of exoplanets, planets around other stars. Although he could not see them directly, Hubble studied the atmospheres of these distant worlds. He found water vapor, sodium, and methane in the atmospheres of planets thousands of light years away. These are the first steps towards the search for life outside the solar system. One of the most eerie and beautiful discoveries of Hubble is black holes in the centers of galaxies. It turned out that almost every large galaxy contains a supermassive black hole at its heart. At the center of our Milky Way is a black hole with a mass of 4 million suns. Hubble helped to understand that these cosmic monsters are not just destroyers. They play a key role in the formation and evolution of galaxies. The telescope captured dying stars in their final act of creation. Planetary nebulae are a death dance as a star the size of our sun sheds its outer shells, creating incredible shapes in space. The Cat's Eye Nebula, the Butterfly Nebula, the Hourglass Nebula. Each is unique, each telling the story of stellar death. The irony is that these beautiful celestial objects are the funeral pyres of the stars. In 35 years of work, Hubble has made more than 1.6 million observations. He studied more than 50,000 celestial objects. Based on his data, more than 20,000 scientific articles have been published. This is more than any other astronomical instrument in history. Each week brought new discoveries, new mysteries. The telescope showed us galaxy collisions, a process that took hundreds of millions of years, but froze in one moment in the images. Antenna galaxies merging in a gravitational embrace. When galaxies collide, the stars almost never crash into each other. The distances between them are too great. But gravity distorts their shapes, pulls long tails out of stars, and triggers frenzied star formation. In a few billion years, our Milky Way will collide with the Andromeda Galaxy. Hubble gave us a preview of this event. He solved the mystery of gamma-ray bursts, the most powerful explosions in the universe after the Big Bang. In a few seconds, a gamma-ray burst releases more energy than the sun does in its entire lifetime. Hubble helped establish that these bursts occur in distant galaxies when massive stars collapse into black holes or when neutron stars collide. Each day of Hubble's work costs about $30,000. The telescope orbits at a speed of 27,000 kilometers per hour, making a full revolution around the Earth every 95 minutes. It can fix an object with an accuracy of 0.007 arcseconds. It's like seeing a firefly at a distance of 12,000 kilometers. Its solar panels, which are the size of a bus wing, generate 5,600 watts of power. The entire telescope weighs 11 tons and is about the size of a school bus. But the most surprising thing is that Hubble is not just observing the cosmos. He changed the culture. His images became part of popular culture, appeared on album covers, in films, on t-shirts. People get tattoos of nebulae taken by Hubble. Space has ceased to be an abstract scientific concept and has become real, tangible, and beautiful. Astronomers have discovered with the help of Hubble that the formation of planets is a common phenomenon. Protoplanetary disks around young stars have been observed dozens of times. This means that the planets are not unique to the solar system. If planets are everywhere, then there may be other forms of life out there. The telescope operates in the harsh conditions of space. Temperature drops from -100 to +100 degrees Celsius. Constant radiation. Micrometeorites rushing at the speed of bullets. Over the years, the astronauts have flown 5 times to repair and improve the telescope. The last mission was in 2009. Since then, Hubble has been operating autonomously, without the possibility of repair. Every year, engineers are surprised that it is still functioning. Recently, one of Hubble's gyroscopes failed. These devices help the telescope to accurately aim at targets. Of the 6 gyroscopes, only 3 work. When another one fails, Hubble's capabilities will be severely limited. But NASA engineers aren't giving up. They've developed new control methods that will allow the telescope to work with even a single gyroscope. Hubble has discovered the most distant objects ever seen by man. GN Z11 is 13.4 billion light-years distant. We see it as it was just 400 million years after the birth of the universe. This is almost the edge of the observable universe, almost the beginning of time. The telescope helps solve the mystery of dark matter. Hubble observed the effect of gravitational lensing, when massive objects bend light from distant galaxies. From the degree of curvature, scientists can calculate the mass of invisible matter. It turned out that dark matter makes up 85% of all matter in the universe. We are made of a rare material, ordinary matter, which is a minority in space. Each Hubble image is not just a photograph. The telescope does not see in the colors that we see. It captures light in a variety of wavelengths, including infrared and ultraviolet. Specialists then combine these images and color them, often assigning colors to different chemical elements. Red can mean hydrogen, green, oxygen, blue, nitrogen. These colors are real, but processed so that the human eye can distinguish the details. Hubble caught the moment when a star named SN 1987A exploded as a supernova. For decades, he watched the remnant of that explosion expand and evolve. Observing a single object for such a long time has given astronomers a unique opportunity to understand the life cycle of stars. A supernova explosion ejects all the heavy elements created inside the star into space. The carbon in our bodies, the oxygen we breathe, the iron in our blood were all forged inside stars and scattered throughout space at the time of their death. We are literally made of stardust. An observatory in orbit has discovered strange objects called quasars, the nuclei of ancient galaxies that shine brighter than trillions of suns. At their center are black holes that are devouring matter at an incredible rate. Matter falling into a black hole heats up to millions of degrees and radiates colossal energy. Some quasars are so bright that their light traveled through the universe for billions of years before reaching us. The device captured a phenomenon that physicists call Einstein's gravitational lenses. Massive galaxy clusters curve space-time so much that light from even more distant galaxies bend around them, creating multiple images or arcs. Sometimes you get a complete ring of light, Einstein's ring. It's not just beautiful. It's a direct proof of general relativity, an opportunity to observe the very fabric of space-time. Hubble traced the life of stars from the cradle to the grave. Young stars, newly born from clouds of gas, surrounded by bubbling disks of matter. Middle-aged stars like our sun are quietly burning hydrogen. Red giants, swollen to monstrous sizes. White dwarfs are cooling embers the size of Earth, but as dense as a teaspoon of their matter, they would weigh tons. And neutron stars are so compressed that atoms are crushed, and matter exists in exotic states that cannot be recreated in terrestrial laboratories. Observations have shown that collisions occur in the universe not only of galaxies, but also of entire clusters of galaxies. The Bullet cluster is two giant clusters that pierced each other at speeds of millions of kilometers per hour. In the collision, the hot gas slowed down and was left behind, but the dark material passed through without interaction. This is one of the most convincing evidence for the existence of dark matter. The orbiter discovered rogue stars ejected from their galaxies into the intergalactic void. Imagine the sun drifting in absolute darkness between galaxies, where the nearest star is millions of light years away. There could be planets around such stars, and if there is intelligent life there, their night sky is completely black without a single star. The data showed that black holes come in a variety of sizes. Stellar black holes with a mass of 3 to several dozen suns are the result of the collapse of massive stars. Supermassive black holes at the centers of galaxies range from millions to billions of solar masses. But there are also intermediate black holes, the origin of which remains a mystery. Perhaps they are formed by the collision of stellar black holes or the seeds of future supermassive monsters. Hubble captured the moment of the star's death not through an explosion, but through an exhalation. Light stars like the sun die quietly. They shed their shells and layers, creating complex, symmetrical patterns. The Snail Nebula looks like a giant cosmic eye looking at us from the depths of space. The central star, now a white dwarf, continues to shine, gradually cooling over billions of years. The images showed the birth of stars in real time, from an astronomical point of view. By comparing images of the same regions taken at intervals of years, astronomers observed changes. Jets of matter gushing out of protostars changed shape. Shock waves propagated through gas clouds. Space has proven to be a dynamic place where dramatic changes are taking place. The device revealed to the world the beauty of planetary nebulae in all its details. Each of them is unique. The Eskimo Nebula looks like a face in a fur hood. The Red Spider Nebula resembles a giant arachnoid with two powerful streams of gas. The Soap Bubble Nebula is a perfect sphere that expands in space. These objects live for only a few tens of thousands of years before dispersing into interstellar space, enriching it with heavy elements for the next generation of stars. Studies have revealed that massive stars live fast and die young. A star with a mass 50 times that of the Sun will live only a few million years, compared to 10 billion years of our Sun's lifetime. But it's these massive stars that create most of the heavy elements in the universe. They burn brightly, create new atoms in the thermonuclear furnaces of their interiors, and then explode, seeding space with the building blocks for planets and life. Hubble helped to understand the structure of the universe itself. Galaxies are not scattered randomly. They form webs, filaments, and walls surrounding giant voids. The Sloan Great Wall is a 1.4 billion light-year structure and one of the largest known structures in the cosmos. The voids between these walls are regions where there are almost no galaxies, just a dark space hundreds of millions of light-years across. Observations of variable stars, Cepheids, made it possible to accurately measure the distances to distant galaxies. These stars pulsate at regular intervals, and the brightness of their pulsations is related to their true luminosity. By knowing the true brightness and the observed brightness, distance can be calculated. These are standard space candles, a space measuring tape. The orbiting observatory recorded a phenomenon called the transit of an exoplanet. When a planet passes in front of its star, the star's brightness drops slightly. From the nature of this dimming, it is possible to determine the size of the planet, its velocity, and even the composition of the atmosphere if the star's light passes through this atmosphere. One of the most exciting moments is the detection of water vapor in the atmosphere of a Neptune-sized exoplanet 120 light-years away. The spacecraft observed comets in our own solar system. As the comet approaches the Sun, the ice evaporates, creating tails of gas and dust millions of kilometers long. Hubble studied the breakup of comets, the moment when the nucleus breaks apart. Comet Ison broke apart as it approached the Sun in 2013, creating a dramatic spectacle. The images showed that even in our solar system, amazing things are happening. Auroras on Jupiter are hundreds of times more powerful than Earth's, caused by the interaction of the planet's magnetic field with particles from the volcanic satellite Io. Geysers on Saturn's moon Enceladus ejecting water into space from a subglacial ocean. Atmospheric changes on Neptune are the appearance and disappearance of the Great Dark Spot, an Earth-sized storm system. Hubble has become a tool for predicting the future. Astronomers used its data to simulate the collision of the Milky Way with Andromeda. In about 4 billion years, the two galaxies will begin to approach each other. The stars of both galaxies will be ejected into new orbits. The supermassive black holes at the centers of both galaxies will eventually merge, creating an even more massive black hole. Two spiral galaxies form one giant elliptical galaxy. But for stars and their planets, it would be a relatively safe event. Collisions between individual stars are extremely unlikely due to the vast distances. Observations of T-Tauri stars, very young stars just 1 million years old, have revealed what our Sun looked like in its infancy. These stars are surrounded by disks of gas and dust from which planets form. They are unstable, throw out powerful streams of matter, and experience dramatic flashes of brightness. Our solar system went through this turbulent phase billions of years ago. The data helped solve the mystery of ultra-compact dwarf galaxies. These objects contain millions of stars packed into a volume just a few hundred light years across. The density of stars there is thousands of times higher than in the vicinity of the Sun. If we lived in such a galaxy, the night sky would be littered with bright stars, many of which would shine brighter than the full moon. The observatory has discovered hypergiant stars, the largest and brightest stars in the known universe. Scuti has a radius about 1,700 times that of the Sun. If you put this star in the place of our Sun, its surface would extend beyond the orbit of Jupiter. These monsters are unstable, losing mass at an incredible rate, and only a few million years before exploding. Hubble has recorded a rare event, gravitational microlensing. When one star passes exactly in front of another from our point of view, the gravity of the near star focuses the light of the distant star, causing a temporary increase in brightness. This effect lasts only a few hours or days. If a nearby star has planets, they create additional bursts of brightness. This is how several exoplanets were discovered. The pictures captured the consequences of stellar collisions. In dense star clusters, stars sometimes get so close that they merge, creating blue wanderers, stars that look too young for their surroundings. They received fresh fuel from the swallowed star and continue to glow bright blue among the old red stars. The device helped to study cosmic jets, streams of matter escaping from the vicinity of black holes at speeds close to the speed of light. These jets stretch for thousands of light years, piercing intergalactic space. The energy of one such jet exceeds the energy of billions of stars. The mechanism of their formation is not fully understood, but is related to the rotation of the black hole and the accretion disk surrounding it. Magnetic fields swirl around the black hole, capture particles, and accelerate them to relativistic speeds, shooting into space like from a cannon. Hubble discovered the existence of stellar streams, long rivers of stars that surround our galaxy. These are the remains of dwarf galaxies torn apart by the tidal forces of the Milky Way. Our cannibal galaxy is constantly devouring its smaller neighbors. Stars from these shattered galaxies now orbit the center of the Milky Way, forming ghostly streams stretching for tens of thousands of light years. Observations have revealed the phenomenon of stellar nurseries on an incredible scale. The Tarantula Nebula in the Large Magellanic Cloud is a star-forming region so active that if it were in the site of the Orion Nebula, the closest starbirth region to us, it would shine brighter than Venus in our sky and cast shadows at night. Hundreds of massive stars are born there at the same time, creating a superstar cluster. The device captured a rare phenomenon, a Type I supernova at the time of the explosion. These explosions occur when a white dwarf in a binary system sucks matter from a companion star until it reaches a critical mass of 1.4 solar masses. Then a thermonuclear explosion occurs, which completely destroys the star. The brightness of all such explosions is about the same, making them ideal standard candles for measuring cosmic distances. It was the study of distant Type I supernovae that led to the discovery of the accelerated expansion of the universe. The orbiting observatory has discovered ghost galaxies, ultra-diffuse galaxies the size of the Milky Way, but containing 1,000 times fewer stars. They are so sparse that they are almost transparent. Through them, you can see the galaxies in the background. Why these galaxies are so ghostly is one of the modern mysteries of astronomy. It is possible that dark matter makes up almost all of their mass, and ordinary matter for some reason could not effectively form stars. The images revealed the complex structure of supernova remnants. The Crab Nebula, the remnant of a star explosion observed by Chinese astronomers in 1054, contains a pulsar at its center that rotates 30 times per second. This dead remnant of the star, which is only 20 kilometers in diameter but densities of billions of tons per cubic centimeter, emits beams of radiation that illuminate the surrounding gas, causing the entire nebula to glow. Within the nebula, dramatic changes occur. Gas knots move at up to half the speed of light. Hubble helped to understand the evolution of galaxies. By comparing galaxies of different ages, astronomers have built up a picture of how galaxies have changed over time. Young galaxies in the early universe were smaller, more irregularly shaped, with more intense star formation. They collided and merged, gradually growing into the massive elliptical and spiral galaxies we see today. The process of galaxy formation is still going on today. It's not a complete story, but an ongoing evolution. The data revealed the existence of isolated black holes drifting through interstellar space. When a massive star explodes asymmetrically, the newborn black hole can receive a powerful boost enough to eject it from its parent cluster. These lone black holes are invisible. They can only be detected when they accidentally pass in front of a distant star, and their gravity bends the light. It is estimated that there may be hundreds of millions of these wandering black holes in our galaxy. Observations of globular clusters, ancient groups of stars orbiting galaxies, have revealed that they contain some of the oldest stars in the universe. Some of the stars in these clusters are almost 13 billion years old, having formed just a few 100 million years after the Big Bang. These stars have survived almost the entire history of the universe. They contain very few heavy elements because they were born before many generations of stars had time to enrich the cosmos with nuclear fusion products. The device recorded the phenomenon of tidal destruction of the star. When a star gets too close to a supermassive black hole, gravitational tidal forces tear it apart. Half of the stellar material falls into the black hole, creating a bright burst of radiation that can last for months. The other half is ejected into space. This is a brutal demonstration of the power of black holes, a cosmic act of cannibalism. Hubble discovered intergalactic stars, stars that live in the void between galaxies and clusters. About 10% of the stars in some galaxy clusters do not exist in the galaxies themselves, but drift in intergalactic space. They were ejected from their home galaxies as a result of gravitational interactions. Planets around such stars would see in the sky not clusters of stars of their own galaxy, but many distant galaxies scattered across the sky. The images showed the detailed structure of the dust disks around stars. The disk around the star Beta Pictoris contains clear signs of planets, gaps in dust, curvatures, asymmetries. The planet's gravity clears space in their orbits, creating dark rings in the disk. This is direct evidence of the formation of a planetary system in real time. The orbiting observatory helped map the distribution of dark matter in the universe. Although dark matter is invisible, it makes up 85% of all matter, and its gravity affects the motion of galaxies and the bending of light. By creating gravitational lensing maps, astronomers were able to see where dark matter is concentrated. It turned out that it forms the cosmic web, filaments, and nodes along which galaxies are located. Ordinary matter simply follows the gravity of dark matter. Hubble observed the birth of planets firsthand. Protoplanetary disks around young stars contain concentric rings and spiral patterns, signs that planets have already begun to form. Dust sticks together into pebbles, pebbles into boulders, boulders into planetesimals, planetesimals into protoplanets. The whole process takes millions of years, but we can observe different stages by studying many systems of different ages. The data revealed the existence of hypervelocity stars, stars moving so fast that they would leave our galaxy. The speed of some exceeds 1,000 kilometers per second. The only known way to accelerate a star to such a speed is through gravitational interaction with the supermassive black hole at the center of the galaxy. The star was part of a binary system that came too close to the black hole. One star was captured, the other was thrown away at great speed. The device studied active galactic nuclei, extremely bright centers of some galaxies, where supermassive black holes actively devour matter. A single quasar can shine brighter than 1 trillion stars, eclipsing its entire galaxy. Matter falling into a black hole heats up to millions of degrees and radiates throughout the electromagnetic spectrum. The power of these objects is so great that they can influence star formation throughout the galaxy by blowing gas away and preventing the formation of new stars. Observations have shown that galaxies grow not only through the gradual accretion of gas, but also through mergers. Large galaxies formed from the merger of many smaller galaxies. The history of the Milky Way includes the devouring of at least a dozen dwarf galaxies. Some of the stars in our galactic halo are immigrants from these long-vanished galaxies. The archaeology of galaxies allows us to reconstruct their turbulent past. Hubble has discovered the most distant galaxies whose light has been traveling to us for more than 13 billion years. These first galaxies were small, only a few percent of the mass of the modern Milky Way. They contained the first generation of stars born from almost pure hydrogen and helium left over from the Big Bang. In these stars, heavy elements were first formed, which later allowed planets and life to form. The images captured the beauty of reflection nebulae, clouds of dust that do not glow themselves, but reflect the light of nearby stars. The Witch's Head Nebula is colored blue because blue light is scattered by dust more efficiently than red light, the same effect that makes our skies blue. These nebulae are art galleries of the cosmos, showcasing the play of light and shadow in the interstellar medium. The orbiting observatory helped identify the sources of gamma rays. Pulsars, spinning neutron stars with powerful magnetic fields, act as cosmic beacons, emitting beams of gamma rays. When the beam is pointed at the Earth, we see regular pulses. The fastest known pulsar rotates 716 times per second. It's a city-sized object that contains more mass than the Sun, making nearly 1,000 rotations every second. The data showed that the massive elliptical galaxies at the centers of the clusters contain trillions of stars. IC 1101, one of the largest known galaxies, has a diameter of about 6 million light-years and contains approximately 100 trillion stars. For comparison, our Milky Way contains only about 200 to 400 billion stars and has a diameter of about 100,000 light-years. These monster galaxies formed through multiple mergers and are located in the centers of gravity wells, where matter from vast regions of space flows. Hubble has observed unusual supernova explosions that do not fit into the known categories. Type Ion supernovae interact with the dense cloud of matter that the star ejected before the explosion. The collision of the shock wave with this cloud creates additional radiation, making the explosion brighter and longer. Some supernovae, called superbright supernovae, are tens of times brighter than normal and can be seen at distances of billions of light-years. The device studied the chemical composition of stars in different parts of the galaxy. Stars at the center of the Milky Way contain more heavy elements than stars on the outskirts. This metallic gradient shows that the central regions of the galaxy have evolved more chemically, with more generations of stars enriching the environment with fusion products. Our Sun is 26,000 light-years from the center and has an average chemical composition for its location. The images revealed binary black holes at the centers of merging galaxies. When two galaxies merge, their central black holes end up in the same system and begin to orbit each other. Over time, they will lose energy through gravitational waves and eventually merge, creating one more massive black hole and releasing a huge amount of gravitational energy. This event will be one of the most powerful in the modern universe. Hubble helped to detect exomoons, satellites orbiting exoplanets. Although direct confirmation is still controversial, the evidence points to the possible existence of Neptune-sized moons orbiting gas giants in other star systems. If confirmed, this would open up a new category of celestial bodies for study. Large moons can have their own atmospheres and even be habitable. The observations revealed stars with exotic chemical compositions. Przybylski's stars contain abnormally high concentrations of rare elements, such as strontium, chromium, and rare earth metals. Their atmospheres exhibit complex chemical irregularities that create spots on the surface. The powerful magnetic fields of these stars, thousands of times stronger than the Sun's, separate the chemical elements, concentrating some of them in certain areas. The orbiting observatory has captured the phenomenon of stellar cannibalism in close binary systems. A more massive star evolves faster and expands into a red giant. Its outer layers flow to the companion star through the Lagrange point. The companion is gaining mass and may even surpass the initially more massive star. This mass exchange radically changes the evolution of both stars. The data revealed the existence of safer galaxies, spiral galaxies with unusually bright nuclei. In the center is an active supermassive black hole that is devouring gas. Some safer galaxies emit powerful streams of ionized gas at speeds of thousands of kilometers per second. Hubble detected the CMB radiation from the early stages of galaxy evolution in the form of halos of hot gas surrounding some galaxies. This gas is heated to millions of degrees and emits X-rays. It is material that has not had time to form stars, and the products of stellar winds and supernovae ejected from the galaxy. The mass of this gas sometimes exceeds the mass of all the stars in the galaxy. The mass of this gas sometimes exceeds the mass of all the stars in the galaxy. It's a hidden reservoir of matter that could fuel future star formation or be lost to intergalactic space forever. The spacecraft studied the interaction of stellar radiation with the interstellar medium. Hot young stars emit powerful ultraviolet radiation that ionizes the surrounding gas, creating regions of HII, clouds of glowing hydrogen. These regions can be huge, hundreds of light years in diameter, and contain enough energy to compress nearby gas clouds, triggering new waves of star formation. It is a self-sustaining cycle of creation. The images showed the structure of magnetic fields in nebulae through the polarization of light. Dust in space lines up along magnetic field lines, and the light passing through it becomes polarized. By analyzing this polarization, astronomers can map the invisible magnetic fields that play a critical role in the formation of stars and planets. Magnetic fields can slow down the collapse of gas clouds or direct streams of matter away from young stars. Hubble discovered stars in the final stages of life, known as RV Tauri variables. These stars are unstable. Their brightness changes irregularly, sometimes tens of times. They are in a transitional stage between red giants and planetary nebulae, shedding matter in gusts. Their unpredictable behavior reflects the chaotic processes in their interiors, where thermonuclear reactions flare up and then fade. The observations revealed the phenomenon of stellar bridges, streams of stars connecting interacting galaxies. As two galaxies approach each other, their tidal forces pull long tails of stars, gas, and dust. These tails can extend for hundreds of thousands of light years. Sometimes new stars and even dwarf galaxies form in these tidal tails. This is the birth of second-generation galaxies generated by gravitational violence. The orbiting observatory studied brown dwarfs, objects that occupy an intermediate position between planets and stars, not massive enough for sustained thermonuclear fusion of hydrogen, mass less than 0.08 solar masses. They nevertheless glow due to residual heat from gravitational compression and short-term burning of deuterium. The coldest brown dwarfs have a temperature of about 100 degrees Celsius, cooler than a cup of coffee. In their atmospheres, clouds of silicates and even water vapor can exist. The data showed the existence of stars with planets orbiting in the habitable zones, regions where the temperature allows liquid water to exist on the surface. Proxima Centauri, the closest star to us after the Sun at a distance of 4.2 light years, has a planet Proxima b in the habitable zone, although the conditions there can be harsh due to flares on the red dwarf. Liquid water could theoretically exist there, which means that life is possible. Hubble captured the death of the star in slow motion. The star Eta Carinae, one of the most massive and unstable stars known, experienced a giant flare in the 1840s, ejecting matter with a mass of several suns. It is surrounded by a bipolar nebula, two lobes of ejected material, each about the size of our solar system. The star is teetering on the brink. At any moment, it can explode as a supernova. When this happens, the explosion will be visible during the day and could rival the brightness of the full moon. The observations revealed star streams in the Milky Way's halo, the remnants of at least 20 ruptured dwarf galaxies. Each stream contains millions of stars slowly smearing in orbit around our galaxy. Over time, these stars will completely blend into the galactic halo, becoming indistinguishable from other stars. This is evidence that our galaxy continues to grow, devouring smaller neighbors. The spacecraft studied Wolf-Rayet stars, massive stars in the late stages of evolution that are losing mass at a catastrophic rate. Stellar winds blow up to solar mass every 10,000 years, exposing inner layers enriched in helium, carbon, and oxygen. These stars are surrounded by expanding shells of ejected material. They end their lives with supernova explosions or collapse directly into black holes without a visible explosion, the quiet disappearance of a massive star. The images showed details in the structure of the jets emitted by young stars. These bipolar outflows are narrowly collimated flows of gas moving at speeds of hundreds of kilometers per second. The collimation mechanism is related to magnetic fields and the rotation of the accretion disk around the protostar. The jets transfer excess angular momentum away from the system, allowing matter to continue falling into the growing star. Hubble helped to understand the nature of ultraluminous X-ray sources, objects that emit X-rays with a brightness that exceeds the capabilities of ordinary stellar black holes. These are probably intermediate mass black holes, between 100 and a few thousand solar masses, or ordinary black holes in a state of supercritical accretion, when matter falls so fast that the radiation exceeds the theoretical Eddington limit. The data found galaxies with 2 active nuclei, the result of a recent merger when both supermassive black holes had not yet had time to merge. They orbit each other thousands of light years away, each absorbing gas and emitting energy. Over time, they will come closer and merge, but this process can take millions of years. The orbiting observatory has studied globular clusters in our galaxy and found that some of them have multiple populations of stars. Previously, it was thought that all the stars in the cluster were born at the same time, but it turned out that some clusters survived several epochs of star formation. The second generation of stars formed from material enriched with first-generation products, which gave them a different chemical composition. Hubble observed stars in extreme environments, in the vicinity of the supermassive black hole at the center of the Milky Way. These stars orbit the black hole in elongated orbits, approaching it at distances of only a few light hours. They move at speeds of up to 5,000 kilometers per second, almost 2% of the speed of light. Observations of their orbits have made it possible to accurately measure the mass of the central black hole, 4.15 million solar masses. The images captured galaxies in the process of transformation. Some spiral galaxies lose their structure due to interactions with other galaxies or due to gas depletion. They turn into lenticular or elliptical galaxies. The process takes hundreds of millions of years, but by comparing many galaxies at different stages, astronomers were able to reconstruct the sequence of evolution. The spacecraft found evidence of the existence of massive intermediate black holes in the centers of some globular clusters. These black holes, with a mass of several thousand suns, may be the remnants of more massive clusters that have been destroyed by the galaxy's tidal forces. They represent the missing link between stellar and supermassive black holes. Observations have shown that some galaxies contain 2 supermassive black holes not because of a recent merger, but because they originally formed with 2 massive nuclei. This calls into question traditional models of galaxy and black hole formation. Perhaps the early universe was more chaotic and galaxies formed from multiple centers of collapse. Hubble studied neutron stars, the remnants of stars after supernova explosions so dense that a teaspoon of their matter would weigh 1 billion tons. Some neutron stars have magnetic fields trillions of times stronger than Earth's. Magnetars, neutron stars with the strongest known magnetic fields, periodically emit powerful bursts of X-rays and gamma rays that can affect the Earth's ionosphere from thousands of light years away. The data revealed the existence of stellar shells around some planetary nebulae, several concentric spheres of ejected material, indicating that the dying star has experienced a series of mass loss pulses, rather than one continuous process. Each shell represents a different episode of instability in the last thousands of years of the star's life. The orbiting observatory has discovered galaxies with a deficit of dark matter, the so-called transparent galaxies, where there is as much or even more ordinary matter than dark matter. This contradicts standard models of galaxy formation, according to which dark matter should dominate. It is possible that these galaxies were tidally ejected from larger systems and lost much of the dark halo. Hubble captured runaway stars, high-speed stars leaving star clusters. When several stars meet in a dense cluster, the gravitational interaction can eject one of them at high speed. These exiled stars travel through the galaxy alone, carrying with them the memory of a dramatic past. Observations have shown that massive stars are rarely born alone. Most are formed in multiple systems, double, triple, or more complex configurations. The gravitational interaction between the components of such systems can radically alter their evolution, leading to mass exchange, merger, or ejection of one of the components. The device studied open clusters, younger and less dense groups of stars than globular clusters. The Pleiades, the most famous open cluster visible to the naked eye, contains several hundred stars about 100 million years old. Over time, the tidal forces of the galaxy will tear the cluster apart, and the stars will disperse in their orbits. Most open clusters have been around for less than 1 billion years. The images revealed stellar nurseries hidden in dense molecular clouds. Ordinary visible light cannot penetrate these clouds, but Hubble's infrared instruments can see through the dust. Inside these cocoons, protostars are forming, still gaining mass from the surrounding material. In 1 million years, they will light up as full-fledged stars, destroying the parent cloud with their radiation. Hubble helped to understand the cycles of star formation in galaxies. Star formation is not constant. It occurs in flares. Massive stars don't live long and explode as supernovae, compressing the surrounding gas and triggering a new wave of star formation. But the same supernovae heat up and eject gas from the galaxy, temporarily stopping star formation. After hundreds of millions of years, the gas cools and returns, starting a new cycle. The data showed the existence of blazars, active galactic nuclei whose relativistic jets are pointed directly at us. Due to relativistic effects, their radiation is amplified and appears extremely bright. Blazars exhibit dramatic changes in brightness on scales ranging from hours to years, reflecting unstable processes near the black hole and in the jet. The orbiting observatory has discovered planetary systems with retrograde orbits, planets orbiting in the opposite direction to the rotation of the star. This points to the system's dramatic history, perhaps a gravitational interaction with another star or a massive planet that flipped orbits. The formation of planetary systems turn out to be a much more chaotic process than previously thought than previously assumed. Some systems have survived close flybys of other stars, gravitational scattering of planets, even collisions of protoplanets. Neat models of planet formation from a quietly rotating disk turned out to be a simplification. The reality is much more messy and violent. The spacecraft observed cooling white dwarfs, stellar corpses slowly giving off their last heat into space. The oldest white dwarfs in our galaxy are about 12 billion years old and have cooled to a temperature of only a few thousand degrees. In trillions of years, they will become black dwarfs, completely cooled, invisible objects. But the universe is still too young for black dwarfs to form. Hubble captured the interaction of the stellar wind with the interstellar medium. As a hot star moves through space at high speed, its stellar wind collides with the surrounding gas, creating an arc-shaped shock wave, like a bow wave from a ship. These arc shock waves can extend for light years, compressing gas and potentially triggering star formation. The images showed galaxies with polar rings, strange systems where a ring of gas, dust, and stars orbits perpendicular to the plane of the main galaxy. These structures are likely formed when one galaxy tidally rips apart another and material is trapped in a polar orbit. The polar rings live for hundreds of millions of years before gradually aligning with the host galaxy. The observations revealed the existence of dark galaxies, clouds of gas the size of a dwarf galaxy, but containing almost no stars. These objects consist mainly of dark matter and gas, but star formation in them for some reason has not begun or is extremely slow. They are invisible in ordinary light and are only detectable by their gravitational influence or absorption of light from background sources. The orbiting observatory studied stars of the Mira type, red giant variables with a huge amplitude of brightness change. In a year, the brightness of Mira can change hundreds of times. These stars pulsate physically, inflating and contracting over a period of several months to several years. During pulsations, they lose significant mass, creating expanding shells of dust around them. The data showed that the satellite galaxies of the Milky Way are not randomly distributed, but lie predominantly in the same plane. This is an unusual configuration that is difficult to explain with standard models of galaxy formation. Perhaps many of the moons were captured as a group during an ancient merger, or they formed from a general stream of matter falling on our galaxy. Hubble found stars with planetary systems aligned not with the star's equator, but at large angles. Some planets even orbit almost perpendicular to the rotation of the star. This indicates that planetary systems can be rearranged by gravitational interactions after they have already formed. It is possible that massive planets migrated into the system, disrupting the orbits of other planets. The images captured the structure of the spiral arms of galaxies in unprecedented detail. Spiral arms are not material structures, but density waves passing through the galactic disk. Stars and gas enter the arm, slow down, contract, which triggers star formation, creating bright young stars that illuminate the arm. Then the stars leave the arm, continuing their orbit. The spacecraft studied symbiotic stars, close binary systems consisting of a hot white dwarf and a cool red giant. The intense ultraviolet radiation from the white dwarf ionizes the giant's atmosphere, creating a glowing nebula around the system. These objects exhibit complex interactions between components, including mass fluxes and periodic flares. The observations revealed jellyfish galaxies, spiral galaxies moving through dense clusters of galaxies so fast that the pressure of intergalactic gas blows away their own gas, creating long tails of star-forming material. These tails resemble the tentacles of a jellyfish. Star formation occurs along the entire tail, creating chains of young star clusters. Hubble helped measure the Hubble constant, the rate at which the universe expands, with unprecedented precision. However, a problem arose. The value measured from nearby objects does not coincide with the value derived from the CMB radiation of the early universe. This Hubble tension is one of the main mysteries of modern cosmology. Perhaps new physics is needed to explain the discrepancy. The data revealed the existence of superclusters of galaxies, structures containing tens of thousands of galaxies spread over hundreds of millions of light years. Laniakea, the supercluster that contains our Milky Way, includes about 100,000 galaxies with a total mass of 100 quadrillion suns. All of these galaxies are slowly falling toward the center of mass of the supercluster, the Great Attractor. The orbiting observatory studied flared stars, red dwarfs subject to powerful bursts of magnetic activity. In a few minutes, the brightness of such a star can increase hundreds of times. These flares emit intense ultraviolet and X-ray radiation, which would be dangerous to any life on nearby planets. Many exoplanets in habitable zones of red dwarfs undergo such outbursts regularly. The images showed the detailed structure of the remnants of new stars, thermonuclear explosions on the surface of white dwarfs. Unlike supernovae, novae do not destroy the star. A white dwarf in a binary system accumulates hydrogen from the companion star to a critical point when explosive thermonuclear fusion occurs. The star sheds its shell, but survives and can repeat the process in thousands of years. Hubble found evidence of an intermediate population of stars in the halo of galaxies. Stars about 10 billion years old, younger than the older halo, but older than the stars in the disk. These stars probably belong to dwarf galaxies swallowed up by the Milky Way in the past. The chemical composition and kinematics of these stars tell the story of early mergers. The observations revealed galaxies with active bursts of star formation, starburst galaxies that are forming stars at a rate hundreds of times faster than the Milky Way. These outbursts are usually caused by galaxy mergers that direct large amounts of gas toward the center, where it quickly collapses into stars. The flare can use up all the available gas in tens of millions of years, after which star formation will stop. The spacecraft studied stellar associations, loose groups of young stars born from the same molecular cloud, but not gravitationally bound enough to stay together for long. In a few tens of millions of years, the association will dissipate and the stars will disperse throughout the galaxy. Our sun was probably born in such an association 4.6 billion years ago, but its stellar siblings are now scattered across the galaxy's disk. The data showed the existence of galaxies with a bar, an elongated structure in the center consisting of stars. About 2/3 of spiral galaxies, including our own Milky Way, have a bar. The bar plays an important role in the evolution of the galaxy by directing gas towards the center, fueling the supermassive black hole and stimulating central star formation. The bar of the Milky Way extends about 27,000 light-years from the center. Hubble captured stellar superclusters, massive, dense groups of young stars containing tens of thousands of stars in a region just a few light-years across. These objects are millions of times denser than the Sun's neighborhood. At their centers, The stars are so close that their atmospheres can touch. Gravitational interactions in such dense environments lead to stellar collisions and mergers. The images revealed interstellar comets, objects ejected from their home planetary systems and traveling through the galaxy. Oumuamua, the first interstellar object discovered, passed through our solar system in 2017. Its elongated shape and unusual trajectory have given rise to many hypotheses about its nature. There are probably millions of such interstellar wanderers drifting between the stars. The orbiting observatory studied cataclysmic variables, close binary systems where a white dwarf absorbs matter from an ordinary star. Matter forms an accretion disk around the white dwarf, slowly spiraling downward. Periodically, the disk becomes unstable, causing a flare, an increase in the brightness of the system by several stellar magnitudes in days or weeks. Observations have shown that mass segregation occurs in the centers of some globular clusters. More massive stars sink towards the center over time due to gravitational interaction, while light stars are pushed to the periphery. The center of the cluster becomes a dense core of massive stars and their remnants, white dwarfs. Neutron stars, possibly black holes. Hubble discovered galaxies with active nuclei hidden behind dense clouds of dust. These camouflaged quasars emit enormous energy, but the dust absorbs optical and ultraviolet radiation, re-emitting it in the infrared. The study of these objects is important for understanding the full picture of the activity of galactic nuclei. Many of them were missed in optical surveys. The data revealed stars with an abundance of rare elements such as barium, technetium, and other products of the S process, the slow capture of neutrons in the bowels of massive red giants. Technetium is radioactive with a half-life of only 4 million years, so its presence in the star's atmosphere proves that nuclear fusion occurred recently and the products were transported to the surface by convection. The spacecraft studied interacting galaxies at all stages of the merger. First contact, when galaxies are just beginning to feel each other's gravity. Close encounter, when tidal tails stretch for hundreds of thousands of light years. A final merger, when the nuclei of galaxies plunge into each other, creating an elliptical galaxy. The whole process takes 1 billion years. The images captured planetary nebulae with double nuclei, the result of the evolution of close binary stars. Both stars reach the end of life at about the same time, creating a complex nebula with 2 sources of ionizing radiation. Sometimes the components are so close that they merge before death, creating a single but unusually massive white dwarf. Hubble helped to understand the role of feedback from active galactic nuclei. Powerful winds and jets from supermassive black holes sweep gas out of galaxies, preventing star formation. This explains why the most massive galaxies contain old red stars and few young ones. Their black holes have grown enough to stop star formation. It's a self-regulating process. More gas, more stars, and black hole grows stronger feedback, less gas stop growing. The observations revealed stars with disks of planetary debris, analogs of the Kuiper Belt and other systems. Collisions between asteroids and comets create dust that can be observed by its infrared radiation. These disks of debris indicate the presence of planets whose gravity perturbs the orbits of small bodies, leading to collisions. The orbiting observatory studied stars on the asymptotic giant arm, the late stage in the evolution of low-mass stars, when they swell up hundreds of times and become extremely bright. In their depths, hydrogen and helium burn simultaneously in thin shells. These stars are unstable, experiencing thermal pulses, periodic bursts of thermonuclear combustion that eject material into space. The data showed that many galaxies have elongated halos of hot gas that extend far beyond the visible disk. This gas is too hot for star formation and can remain in the halo for billions of years. It is a reservoir of matter that slowly cools and falls onto the galaxy, fueling future star formation. Without this reservoir, galaxies would have long ago exhausted their gas and died. Hubble captured gravitational arcs, distorted images of distant galaxies whose light passed through a massive cluster of galaxies. The gravity of the cluster acts like a lens, stretching the image of the background galaxy into an arc or even a full ring. The effect makes it possible to study galaxies so distant and faint that they would normally be invisible. The lens naturally amplifies their light tenfold. Some galaxies are seen in multiple copies at the same time. The light came in different ways around the lens cluster. The spacecraft detected stellar fountains, streams of cold gas falling back into galactic disks after being ejected by supernovae and stellar winds. The gas rises thousands of light years above the disk, cools, condenses into clouds, and falls back like cosmic rain. This cycle mixes matter between the disk and the halo, spreading heavy elements and regulating star formation. The images showed the structure of filaments in nebulae, thin filaments of gas that often mark the boundaries of shock waves from supernovae or the boundaries of expanding HI regions. These filaments can be light years long, but only a few astronomical units thick. Magnetic fields and density inhomogeneities create these delicate structures, visible only thanks to the exceptional resolution of the orbiting observatory. The observations revealed the existence of blue stragglers, objects that look too young and hot for their surroundings. In old star clusters, where all stars should be red, these objects shine with a bright blue light. Explanation: they formed through the merger of two smaller stars or received fresh fuel by sucking matter from a companion. This is a second youth through celebrity cannibalism. Hubble studied stellar nurseries in the Orion Cloud, the closest large star-forming region to us, at a distance of 1,500 light-years. There, thousands of stars are born simultaneously in a giant molecular cloud containing tens of thousands of solar masses of gas. Proplyds, protoplanetary disks around young stars, are visible in detail, showing the initial stages of the formation of planetary systems. Powerful ultraviolet radiation from the massive stars at the center of the cluster slowly evaporates these disks, limiting the time available for planets to grow. The data found dwarf elliptical galaxies, compact systems containing millions of stars but devoid of gas and dust. They may be the remnants of larger galaxies torn apart by the tidal forces of their giant neighbors. Or it could be a separate class of originally small galaxies that quickly used up all their gas in an early burst of star formation. The orbiting observatory captured the shadows cast by dense clouds of dust in the nebulae. The cones of shadow extend for light years, creating dark fingers against a background of glowing gas. These structures are like the sun's rays breaking through clouds, only on a cosmic scale and created by starlight. Hubble helped measure the masses of black holes at the centers of galaxies by observing the motion of stars and gas near them. The velocity of revolution of matter is directly related to the mass of the central object. It turned out that the mass of the central black hole is about 0.1 to 0.2% of the mass of the stars in the bulge of the galaxy. This remarkably accurate correlation points to a deep connection between the evolution of the galaxy and its black hole. The images showed ring galaxies, unusual systems where stars and gas form a ring around the center. Such structures are formed in a head-on collision of galaxies, when a smaller galaxy pierces the center of a larger one. The shock wave spreads outward like ripples on water, compressing the gas and triggering a star-forming wave that creates an expanding ring of young stars. The observations revealed stars with extremely low metallicity, almost pure hydrogen and helium, with negligible amounts of heavy elements. These rare objects belong to the second generation of stars in the universe, formed from material slightly enriched by the first stars. Studying their composition provides a window into the chemical evolution of the early universe. The spacecraft has found evidence of star streams inside dwarf galaxies, evidence that even these small systems are devouring even smaller neighbors. Dwarf galaxies engage in the same hierarchical merger game as large galaxies, only on a smaller scale. The data showed the existence of galaxies with depleted nuclei, central regions where the density of stars is lower than expected. Is the result of the merger of two galaxies, each with its own supermassive black hole. When black holes form a binary system and spiral closer to the center, their gravitational interaction ejects stars from their cores, creating a rarefied region. Hubble studied RR Lyrae variable stars, pulsating, low-mass stars used as standard candles to measure distances within our galaxy. Their pulsation period, usually less than a day, is associated with absolute luminosity. By observing these stars in globular clusters, astronomers have accurately determined their distances and ages. The images captured jets from newborn stars called Herbig-Haro objects, where collimated streams of gas from protostars collide with their surroundings, creating glowing shock waves. These objects are ephemeral by astronomical standards, having existed for only a few thousand years. By comparing the pictures taken with a difference of years, you can see how the jets move and evolve. The orbiting observatory has discovered galaxies with multiple star-forming nuclei, not concentrated in the center, but scattered throughout the disk. This is typical for interacting or irregular galaxies, where gravitational perturbations have compressed gas in many places at once, creating multiple bursts of star formation. Observations have shown that some planetary nebulae have a bipolar structure with an equatorial torus, the shape of an hourglass or a butterfly. This indicates that the central star was in a binary system. The companion or accretion disk directed the ejection of matter along the axis of rotation, creating two polar lobes, while the equatorial disk slowly expands outward. Hubble has helped us understand the nature of ultra-compact HII objects, tiny regions of ionized hydrogen around very young, massive stars. These regions are so dense and compact that they represent the earliest phases of a massive star's life, when it is just lit up and begins to ionize the surrounding cocoon. The data revealed the existence of stellar disks around some red giants, a surprising discovery because these stars have already passed the main sequence stage. The disks probably formed from material sucked from a companion or from the remnants of a planetary system destroyed by an expanding star. The device studied Cepheids, pulsating supergiants, whose pulsation period is directly related to their true luminosity. This dependence turned Cepheids into cosmic measuring rulers. By observing Cepheids in distant galaxies, astronomers have built a ladder of cosmic distances that stretches for tens of millions of light years. The images showed antenna galaxies in the process of merging, two spiral galaxies with long, tidal tails that resemble insect antennae. In regions where gas clouds collide, rapid star formation occurs, and thousands of massive stars are born. In hundreds of millions of years, this pair will turn into a single elliptical galaxy. The orbiting observatory has detected stars ejected from the center of the galaxy by the gravitational slingshot of 3 or 4 interacting bodies. The observations revealed evidence that the first galaxies in the universe were dwarfs that gradually merged to form larger systems. Ancient galaxies look smaller, more irregular, and more numerous than modern ones. The hierarchical formation of structure, small objects merging into large ones, is the main paradigm of cosmology. Hubble has captured stars at various stages of mass loss. Some lose matter in the form of a slow stellar wind. Others eject shells and pulses. Still others create bipolar outflows. The variety of ways in which stars die reflects the diversity of their masses, compositions, rotation, and the presence of companions. The data showed that galaxies in dense clusters evolve differently than isolated galaxies. Interactions with other galaxies, tidal disruption, and the removal of gas by the pressure of the intergalactic medium all change galaxies and clusters. They are more likely to become elliptical, lose gas, and stop forming stars earlier than their isolated sisters. The spacecraft studied regions with suppressed star formation in the centers of some galaxies. Despite the high density of gas, stars do not form. Perhaps the turbulence created by the active galactic nucleus or strong magnetic fields are preventing the gravitational collapse of the gas. The central black hole paradoxically prevents star formation in its vicinity. The images revealed star shells around some elliptical galaxies, concentric arcs or rings of stars. These structures are formed when a smaller galaxy falls into a larger one. Stars from the smaller galaxy oscillate through the center of the larger one, creating a wave pattern of stellar density, cosmic ripples from an ancient collision. Hubble helped determine the cosmic abundance of elements in different eras of the history of the universe. By analyzing the spectra of distant galaxies, astronomers measure how much oxygen, carbon, nitrogen, and other elements were in the gas billions of years ago. The universe becomes increasingly chemically enriched over time, as generations of stars create and distribute heavy elements. Observations have shown the existence of supermassive stars in extreme environments, stars with a mass of more than 100 suns teetering on the edge of stability. These giants are so bright that the pressure of their own radiation almost tears them apart. They lose mass at an incredible rate and live for only 1 million years before a catastrophic end, possibly a pair-unstable supernova that completely destroys the star, leaving no remnant. The orbiting observatory has discovered galaxies with holes in the distribution of stars, not central depleted cores, but real voids in the disk. These holes could be created by a dwarf galaxy passing through the disk whose gravity cleared a corridor, or they could be regions where gas was swept away by a supernova explosion or a burst of star formation. The data revealed stars with double or triple periods of variability, complex pulsators where several modes of oscillation overlap. Analyzing these variables allows astronomers to look inside the star. Different modes of pulsations penetrate to different depths, providing information about the structure of the stellar interior. This is stellar seismology. Hubble studied the interaction of galaxies with the intergalactic medium. Galaxies are not isolated in a vacuum. They're immersed in rarefied but extremely hot gas that fills the space between galaxies and clusters. The galaxy's movement through this medium creates shock waves and removes its own gas, a process called pressure stripping. The images captured stellar shells in the process of expanding from new stars. By comparing images of one new one, taken at intervals of years, you can see how the shell expands in space. The expansion rate reaches thousands of kilometers per second, and the shell becomes more and more rarefied until it merges with the interstellar medium. The spacecraft discovered stellar bridges between the Magellanic Clouds, dwarf satellite galaxies of the Milky Way. The gravitational interaction between the clouds has pulled out the streams of stars connecting the two systems. Moreover, there is the Magellanic Stream, a huge plume of gas torn from the clouds and coiling around our galaxy, a plume of gas torn from the clouds and wrapping around our galaxy. This stream stretches for 600,000 light years and contains a mass of gas equivalent to 1 billion suns. The orbiting observatory has completed measurements that have changed our place in the universe. Before Hubble, we knew about the existence of billions of galaxies theoretically. He showed them to us. Before him, exoplanets were a hypothesis. He helped confirm their reality. Before him, dark energy was unknown. It led to its discovery. For 3.5 decades of operation, this device has survived 5 repair missions, many equipment failures, and critical gyroscope breakdowns. Engineers were constantly coming up with new ways to extend its life. Every year, experts predict that this is the last year of operation. But he continues. Now a successor is working in orbit, the James Webb Space Telescope, looking even deeper in the infrared range. But Hubble is not obsolete. He sees in optical and ultraviolet light what Webb cannot. The two instruments complement each other to provide a complete picture of the cosmos. Someday, the gyroscopes will finally fail. Solar panels are degrading. The orbit will begin to descend. At some point, the connection will be cut forever. Decades later, the spacecraft would enter the atmosphere and burn up, ending its journey with a bright flash over the planet it showed the universe. But the legacy will remain. More than 1.5 million pictures, tens of thousands of scientific discoveries, generations of people inspired by his images to explore space. Children who looked at the pillars of creation and decided to become astronomers. Artists who found a source of creativity in nebulae. Ordinary people who have realized the scale and beauty of the universe. Hubble proved that we live in an age of miracles, that you can send an instrument over the atmosphere and see the birth of stars, the death of galaxies, the edges of time, that human curiosity and ingenuity can overcome any obstacle, even a catastrophic mistake in the main mirror. Hubble's images remind us of our insignificance and greatness at the same time. We are tiny creatures on a small planet around an unremarkable star on the outskirts of an ordinary galaxy. But we are able to understand the universe. We can look at light that has traveled for billions of years and decipher its message. We are unraveling the laws that govern trillions of galaxies. Each image is not just a beautiful picture. This is evidence of what happened a long time ago in places so far away that our minds can hardly cover distances. This is proof that the cosmos is not a dead void, but a living, dynamic, ever-changing theater of cosmic dramas. Stars are born and die. Galaxies collide and merge. Black holes devour matter and emit jets of energy. Planets form around distant suns. And it's possible, though we don't know for sure yet, out there that intelligent beings are looking through their telescopes and asking the same questions about their place in space. Hubble did not answer all questions. It has spawned thousands of new ones. What is dark energy? How did the first stars form? Is there life on exoplanets? What happens inside black holes? Each discovery opens the door to new mysteries. This is the essence of science. The more we learn, the more we realize how little we know. But the journey continues. New telescopes study space. New technologies allow you to see what was previously invisible. The next generation will discover things we never dreamed of. Perhaps they will find signs of life in the atmosphere of a distant planet. Perhaps they will see the very first stars ignited after the Big Bang. Perhaps they will unravel the nature of dark matter and dark energy. But all this is built on the foundation laid by Hubble. He taught us to look. He showed that it was possible. He proved that investments in fundamental science bring dividends in the form of understanding, inspiration, and technology. The old telescope continues its lonely dance in orbit, pointing its single eye at the stars. Every night, though there is no night for it, just an endless alternation of light and shadow as it orbits the Earth. It collects photons that have traveled through space for millions or billions of years. These photons began their journey when there was no Earth, no sun, no people. They have crossed unfathomable distances, survived the expansion of space, escaped being swallowed up by dust, and finally reached the mirror of the telescope. There they turned into electrical signals, were transmitted to Earth, and became images on screens. And someone looks at these images, a scientist at an observatory, a student in a classroom, a child on a tablet, and they see not just colored dots, but history. The story of a star born in the chaos of a gas cloud. The history of a galaxy that has lived for billions of years. The history of a universe itself, from the moment of its birth to the present day. Hubble is a bridge between our tiny island of life and the endless ocean of space. This is evidence that the human imagination can stretch as far as light travels in billions of years. This is a monument to curiosity, perseverance, and the desire to understand our place in the grandiose cosmic history. When the last signal stops and the connection is cut off forever, something important will remain. Not just data and images, although they are priceless. What will remain is the knowledge that we are capable of great things. That we can look into the abyss of space and time and not be afraid but surprised. That the beauty of the universe is available to us if we are brave enough to seek it. Hubble changed us. We can no longer think of the universe as something distant and abstract. It's real, it's beautiful, it's full of wonders. And we are part of this incredible story, unfolding over billions of years among trillions of stars.